Okay, we'll continue discussing the energy equation the rest of the class and also somewhat next class. And let's see how we compare how the energy equation can be compared to the Bernoulli equation. So recall that we had for the case of steady and 1D situations, and let's add in addition that we have, say, no work. Okay, and let's write the energy equation for that case. We have m dot, and it was u out minus u in, then the pressure over rho density out minus pressure over rho in, plus v out squared minus v in squared over 2, plus g z out minus z in. And we said there's no work, and so we only have heat. Okay, q net in. So we assume, yes?
After the internal energy, is that plus rho v over rho minus?
Oh, yes, I forgot my operator there. Thank you. It's a plus, yes. So now we assume that in addition that the fluid is incompressible. So rho is equal to a constant. And divide by mass flow rate. And we get. So we're going to do that and also rearrange a little bit. We're going to put all the out terms together and all the in terms together. And so let's put the out terms. We have P out over rho is a constant, plus V out squared over 2, plus G Z out. All of the in terms have a negative sign, so I'll move them to the other side of the equation, equals to P in over rho plus V in squared 2, and then G Z in. But we still have the internal energy terms. I've moved them all to the right hand side, and so minus U out minus U in, and we still of course have the heat term that I've divided by mass, so I'm going to use the lowercase q to indicate heat per unit mass. And since I have a minus sign out here, I'm also going to have a minus sign in here, and this is going to be lowercase q for heat per unit mass. And so heat transfer per unit mass. So you see here that it's very interesting. It looks very much like the Bernoulli equation. Except for these terms here on the right. Now, if the flow were inviscid, we could use Bernoulli equations between the two stations 1 and 2. Or out and in. And write PO, so Bernoulli equation, let's just write it in its usual term, rho VO squared over 2 plus gamma ZO equal to P in plus rho V in squared over 2 plus gamma Z in. And of course here we could divide by rho to get something similar to the equation above. We can compare now. And so we can conclude that in steady, incompressible, inviscid 1D steady flow, I said steady already, so 1D flow, we would have to require that U out minus U in minus Q net in equal to 0. For these two to apply. So Bernoulli equation demands that in my energy equation I make all of those other terms 0. If Bernoulli equation applies, then in the energy equation I must make all of these other terms equal to 0. But this is because we're demanding the situation to be steady, incompressible, and inviscid. Now, if we have friction effects, viscosity, then we would have that U out minus U in minus Q net in is greater than 0. And this is basically an expression of the second law of thermodynamics. Is that good, everyone? Yeah? Okay, so look at this again. This equation here. In the case of ideal flow with no viscosity, all of this guy over here has to be 0 because for Bernoulli equation to apply it has to be 0. If there are friction effects, basically losses, then this term is not 0, it's positive. And for that reason, the sum of these three quantities, P over rho V squared over 2 plus GZ, is what we call in fluid system the useful energy. So this quantity P over rho plus V squared over 2 plus GZ is called useful or available energy. Available to do work. This is what we care about in engineering systems. We want to be able to generate some work. So the other term that appears in this form of the energy equation that we just had, the term U O minus U in minus Q net in, basically this represents the loss of available energy which results in an incompressible flow due to friction. So this term equals the loss. Basically, we're saying if frictionless flow is the same as saying that the loss is equal to 0. Now, in the previous discussion, we simplified our lives by assuming that there is no shaft work, but we can bring that back in now. So if there is shaft work done, we can write again our energy equation, P out over rho, V out squared over 2, G Z out equals P in over rho plus V in squared over 2 plus G Z in, and we have shaft work, but we divided by unit mass, so sorry, by mass flow, so I write it this way, minus the loss, this term over here. And this guy is called the mechanical energy equation, or sometimes also the extended Bernoulli equation. Extended to the case where the flow is no longer inviscid. And so we see that when work goes into the control volume, or in other words, W dot shaft is greater than 0. This is the situation of a pump. Then we could have work going out of the control volume. So W dot shaft less than 0, for example, the case of a turbine. And if we look back at this equation over here and think about these two situations, we realize that if we have a larger loss, then it means that we would require more work in the pump for example, increasing the velocity of the fluid or increasing the elevation of the fluid or doing whatever it is that we want to do with the fluid. If we have more losses, we would require more pump power to produce that effect on the fluid. And if we had more losses in the case of the turbine, it means that we are going to be able to get less work from the fluid system equally for a given change in elevation or a given fluid velocity that we have. We're going to be just getting less work, useful work. So this is one of the main design objectives that we have as mechanical engineers is to minimize the losses and keep losses as small as possible so that we can get more power, say, from a turbine, or be able to elevate fluid with less power into the pump, and so on. So let's just take note of that for your larger losses means more work required to pump, or less work obtained from a turbine. Now note also back in this equation that it has the units of energy per unit mass, right? We can see it clearly in this term, work per unit mass. Energy per unit mass. If we divide by gamma and multiply by rho, we can get in energies of length. So we're going to do that. But I'm going to clear the slides after you finish taking notes. Some of you are still writing. So I'll give you a first, okay. Not yet. So what we're going to do is, so the equation that we just had, the equation of mechanical energy, has units of energy per unit mass. So now, divide by gamma, and multiply by rho, to get P over gamma, P out over gamma, plus V out squared over 2G, plus Z out equals P in divided by gamma, plus V in squared divided by 2G, plus Z over, yeah, what's going on upstairs? They're moving tables and chairs insistently. And we're going to write the terms of work with the capital letter H, because now this is units of length, and so we go back to this terminology of head. Pressure head, remember pressure head, elevation head, and velocity head. Now we have the mechanical energy equation in terms of head, and so we can write HS minus HL, and this guy here is the shaft work head. So measuring the work that we can get from rotating devices in terms of an elevation. And this is the head loss. So in other words, what we just discussed before about the pumps and turbines, pump is a situation where the shaft work head is greater than 0 because work goes into the control volume. In a turbine, HS is smaller than 0 because work comes out of the control volume. And recall that for a fluid system, we called the total head as, well, we can use the capital letter H equals to P over gamma plus V squared over 2G plus Z. So now we can have the simplest possible form of the mechanical energy equation, which is H out equals H in plus H due to work, shaft work, minus head loss. This is the energy equation in terms of head, and it can make things very simple when you're studying fluid systems involving shaft work. And of course things like losses in pipes. So you can imagine a complicated system could have a pump, piping systems where there are losses, a turbine in another location, more pipes, and so on for the whole system. Then you can study everything in terms of the fluid head. Okay. So now let's look at the situation. We've assumed so far all the time that we can take the velocity and all of those properties to be uniform across the control surface. And now let's look at how we can work with non-uniform flows. And so that's the situation when there is a velocity profile at a section of the control surface. And in that case, we need to approximate the surface integral. This term that was the integral across the control surface of, let's look at the velocity one. There's a velocity profile. I'm talking about a velocity profile. So we have v squared over 2 rho, and we have v dot n, the general one with the outward looking normal and a differential of area. So we want to approximate this. We still have one inlet and one outlet. But for whatever reason, we can't really approximate to a uniform velocity profile. So what we do is that we approximate this integral by writing m dot, and we introduce a coefficient. So we're going to write this alpha out, v out squared over 2 minus alpha in, v in squared over 2. And we've introduced this term, this coefficient alpha. This is called the kinetic energy coefficient. So since engineers, we're always trying to make our life easier and finding the simplest way to solve things. And I made a mistake in the sense that I didn't actually add a bar on top of the velocities, because we're going to be dealing now with average velocity to be able to use that form. Of course, because velocity inside the integral was a variable that changes with a certain distribution. So now we use the average velocity. So in general, we write m dot alpha v squared over 2 for the terms over an area v squared over 2, where v now, this v here is a variable. This is, I forgot my bar, v dot n dA in general. So the kinetic energy coefficient is really equal to the integral over the area of v squared over 2 v dot n dA divided by m dot v bar squared over 2. And for uniform flow, of course, alpha is equal to 1, and the velocity is constant, so the average velocity is very easy. But in general, alpha is greater than 1. For example, typical values are alpha, typical values, alpha equal to 2 for a parabolic velocity profile that we can sometimes have inside a pipe, for example. And this is quite tricky, because if we're dealing with a parabolic velocity profile and alpha is equal to 2, it cancels out this 2 here in the equation, so you may be a little bit tempted to think that there's a mistake in the equation. It cancels out the 2, okay? So you have to be careful to know that you're using the kinetic energy coefficient in that case. And and you know, write things out explicitly and cancel them towards the end, perhaps, to make sure that everything is clear. Alpha equals to 1.08 is a value that is common for the case of turbulent, completely turbulent pipe flow. So you see it's a correction which, for completely turbulent pipe flow, this doesn't really introduce that much of a difference, but it could be important. So it's good to know, and we will see how to use it. So there's time to do some applications. So we could write the energy equation with this alpha now. I didn't leave space to write the whole energy equation, but you can see that the whole energy equation for a non-uniform velocity profile will simply have the same terms, P over rho, and the term velocity squared over 2 will have this alpha in front of it, and the velocity is velocity bar, simply. So you can see how we can now rewrite the energy equation for a non-uniform velocity profile. But let's, without further discussion about this, let's look at some applications. So here is a situation that we're going to see about 3 typical applications of the energy equation, and we'll look at some other ones. I mean, 1 today, 2 other ones next class. So this is the typical case where we want to calculate the pressure in a pipe. So consider that we have a horizontal pipe, like shown in this sketch, which is carrying, in this case, is cooling water, say, at 10 degrees Celsius. So we have water for cooling purposes in a, say, production plant at 10 degrees Celsius, or for a power generation plant or something, you have some cooling water. And we have here the geometrical data given in the sketch, an elevation at the surface of the big tank of cooling water of 100 meters. The elevation of the center line of the pipe is at 20 meters. There's a length of pipe, 200 meters, and that's it. But we're also going to be given something additional, something we will study in more detail when we go on to study pipe flow specifically. We have a whole section of the course on pipe flow. But for the time being, we are given that there's head loss in the pipe in the form of the following relation. HL for head loss is equal to some coefficient, in this case 0.02, multiplied by L over D and V squared over 2G. Where L, of course, is the length of pipe, given here. D is the diameter, and say the diameter is given here. No, it isn't, so I'll give it to you here. Diameter equals 20 centimeters, and V is equal to a mean velocity. What else? We're given also some other data. We're given that the rate of flow in this pipe is equal to 0.06 cubic meters per second. And here we're just going to assume a uniform velocity profile, or alpha equal to 1. Okay, so energy equation in normal form, and the question is find the pressure in the pipe. P2. Go to our sketch. So we are going to first do energy equation between 1 and 2. As shown in the sketch. We'll use it in terms of our head loss. We're given head loss, and so we'll use the energy equation in that form. P1 over gamma plus, it gives you the opportunity to write the full energy equation for non-uniform velocity profiles here. So I'll write alpha 1 V average 1 squared over 2G. Of course, alpha is equal to 1, but we'll just write it here, Z1 equal to P2 over gamma plus alpha 2 V average 2 squared over 2G plus Z2. You can see the elevation here is going to play a role, and we have the head loss. So let's we can simplify some things. P1 is equal to 0. Gauge. V1 is equal to 0 because it is at the surface of this tank here, so we assume it's moving it's moving almost 0. We can approximate that. Z1 is, that's given, the elevation is 100 meters. Z2 is also given, it's 20 meters. And V2 we can find using the flow rate. We're given the flow rate. So we need to find this guy. The flow rate is the volumetric flow rate, right? So it's Q divided by the area gives me the mass. And for the area I have the diameter, so I can do that. Okay, fine. So we have 0.06 meters cubed per second divided by the area of that cross section, pi over 4, and 0.2 meters squared. Here's the diameter, and that gives you 1.91 meters per second. So we have V2. P2 is what we need to find. So basically we're almost there. We need to obtain the head loss, but we're giving a relationship for that. So head loss, let's see if I can fit it in this little space here. Head loss is equal to 0.02 L over D V, was it squared? Yes, squared over 2G. So 0.02, and L over D, L is 2,000 meters divided by 0.2. The meters go away, so I don't need to write them down, and I've already found V2, 1.91 meters per second squared divided by 2, and G is 9.81 meters per second squared. So you see we can find that. We know all of those values, and I have the result here in my notes. It's 37.2 meters. Yes, question. It's a square. Sorry for my lousy handwriting. It's a square. Again, lousy handwriting. It was a square. But you can always check that with your units, right? We can almost now solve for P2, right? So we can put in the equation the elevations. We can put that pressure is 0, and this we know, and we can put this term here, and you can see that we know everything. Is it okay if I skip that part and just write the result, and you can check it afterwards? Right? Yeah, okay, you can see that you know everything here. I'll give you the results as I have obtained it. P2 is equal to 418 kilopascal. And do check these things when you go over the lectures, and so you should check those exercises again, right, to make sure that you've followed everything and you're happy with it. Okay, so we have time to get started with one more. We can finish it next class if necessary, but let me just get started with it, which is the power needed by a pump. So we do the classic ones, right? We just looked at just a simple piping system with no devices. Now we look at a pump, and the next one we're going to do is obviously a turbine. Okay? So here's the situation, and I'll give you a little time to make a sketch in your notes with all of these values. And in case you can't read it, it's a bit small. At the entrance of the pump, we have station 1 with an elevation of 30 meters, pressure given there, P1, 70 kilopascal gauge. Alpha 1 is 1. Here we're given, like you were asking, right? We have two situations and we're given alpha 1 and alpha 2. They're both 1, but they could have given you a different number, 1.8 or something, right? It would be possible as well. And you're also given again the flow rate. Q is 0.5 cubic meters per second. And we have a pump. Then we have at the exit of the pump a pipe of 0.5 meters of diameter, and you're given the head loss as a total number. There's a total head loss that's already been calculated for you for this pipe system, and it's 3 meters. And then station 2. Elevation is 40 meters, so we've raised the water by 10 meters. Pressure is 350 kilopascal gauge, so we've raised the pressure of the water quite a bit. And alpha 1 is 1 again. So in addition, it's like the previous case, we have water at 10 degrees. And Q is already given there, 0.5 cubic meters per second. And the pipe is obviously used to move the water from the elevation at 1 to the elevation at 2. And the conditions are all given, and we are giving also the head loss. Good. So now the question is, of course, what power must be supplied to the flow by the pump. So we write the energy, like before, we write the energy equation between points 1 and 2. I'll write it in the form of head because we're giving head loss, so everything is going to be in units of length. So P1 over gamma plus alpha 1 V1 bar squared over 2 plus Z1 and okay, so I'm going to put here the head loss of the pump specifically on this side of the equation with a plus sign. Because remember we were saying that for a pump, it is work that goes into the control volume, and for a turbine it is work that goes out of the control volume. And so we could, in general, and let me finish writing the equation, and I'll answer your question. I saw your hand. Let me just finish writing the equation. We could, in general, write the power of the pump as going in and the power of the turbine as going out. And this is a positive number. I'll just place it in the right spot. And P2 over gamma plus alpha 2 V bar 2 squared over 2 plus Z2. There's no turbine, but I would have put it in this place, and we have the head loss. Yes, your question.
Is there a G under the alpha squared?
Yes, you're very good at catching all my typos. Thank you. Somebody is paying attention.
Write the same equation for a pump and turbine in the same place. But HT on
I would put HT on the right-hand side. And that follows the a couple of slides ago we wrote pump, you know, HS is always positive and turbine is, so it's just looking at work going in and work going out and figure that out so that for the pump it's always going to be like this here. For the turbine, which is the next example we're going to do, next class we're going to write the H turbine on the right hand side going out. Head loss also goes out, right? It's energy that is simply going out of the system into simply heat or forms, you know, friction. It's just absorbed into the environment in some form. Let me just finish up this part of the problem by writing the result for the pump shaft head, which would be equal to P2 minus P1 over gamma plus C2 minus Z1 plus HL. You can see I've just simplified things here. And this term disappears, the term with the velocity disappears because the velocities are equal everywhere in section 1 and 2. The pipe is everywhere, has the same diameter. They haven't told us of two different diameters, and so these two terms are the same, V1 equal V2. And this is the equation that I have, which now I can put all the numbers. So look at this one here now. Now this one, now when I rearrange terms here, I have P2 minus P1, which is out minus in the energy equation, with the positive pump shaft head on the other side. You see? Does this one make sense? This result here? So by rearranging now, we've gone back to the original equation, the original form that we had. You see? So you can see that all of these things are known, and I see you are eager to go to your next class, and so I'll just write down the result here. These pressures are known, 350 minus 70, it's all in kilopascal, and divided by gamma. I would have to look that up for water at 10 degrees. The distances are known also. The distance between Z1 and Z2 is 10 meters. And the head loss is also given 3 meters, and I can obtain my result here for the pump head as 41.5 meters. So we've not quite finished with this problem because the question is power, and so we've only obtained the pump head, and we need to do some conversions and get the mass flow in to get the power. We'll do that next class and then continue with the turbine example.